start this lecture with record. All right. Okay, so the basic definition that we all learn in grade school or high school or whenever about exponents is this, that our definition of exponents or exponentiation is repeated multiplication, right? And we usually see exponents written like so. They take on this form, b raised to, I'm going to put x here, where we have a sort of a larger number at the bottom that we call the base, and sort of a smaller number in the upper right-hand corner called a superscript, right? And we refer to this as either the exponent or the power. In other countries like Britain, they refer to this as the index. And that makes a lot of sense for something we'll learn later on. But in any case, we traditionally refer to it as either the exponent or the power. This is b, whatever the base is, raised to the power of x. And basically what this is telling you is that b to the x means that we're going to take the base b and write it over and over again, but we're going to multiply those bases, dot, dot, dot. And the number of copies of the base that we have that we're multiplying is we have x number of copies of the base b, which is multiplied by itself. Okay. So we can start off with a really simple property of exponents, probably the most basic one, the power of 1. Can anybody tell me what, for example, 2 raised to the first power is?
2.
Yeah, right? Because if this is the base, and this is the number of copies of the base that we need to write, well, then we'll just write the number 2. Okay. So let's say I had -4 raised to the 1 power. What should that be?
-4.
Yeah, -4. And here, once you apply that power, you can drop the parentheses because we're just talking about 1 copy of -4. In general, if we have x, some number or some variable raised to the first power, what should that equal?
That number?
Yeah, whatever that number is. So in this case, we'll just say x. Right, and it doesn't matter if these are whole numbers, positive or negative. It could be, for example, let me give you a third example, a fraction like 1/2 raised to the 1 power. What should that be?
1/2?
Yeah, just 1/2, because we're just writing a single copy of whatever that is. Another example, maybe 0.25, right? This works for decimals as well, raised to the 1 power. What should that be?
0.25.
Yeah, 0.25 or 0.25. Not too scary, right? It seems pretty intuitive that x to the 1 power is equal to x, right? Okay, well, since exponents are sort of like shorthand for repeated multiplication, sometimes we might need to, well, multiply two things together that have different exponents. So for instance, we have these, what we call the product rule. Okay. So if I had, for example, 2 times 2, let's say 2 to the second power times 2 to the third power. Could we rewrite this in terms of an exponent where we sort of combine the exponents and just have a single expression with one exponent? And I said a lot of words there.
2 to the 5th power?
Yeah, 2 to the 5th power. Why should it be 2 to the 5th power, though?
Because you're just adding the exponents.
Yeah, but how do you know to add the exponents? You just like remember from some previous like education, right?
Yeah.
Is it like combining the like terms, or is that the wrong?
Yeah,
word?
it's like you're combining all of the bases together, because if we think about these two terms that we're multiplying together, this guy is really 2 times 2, right? And then we're multiplying that by this guy, which is 2 times 2 times 2. So if we're looking at repeated multiplication here anyway, we're repeatedly multiplying the exact same base how many times? Well, there are 5 copies of 2. So we can simplify that expression and write it as a single exponent here as 2 to the 5th. So there's some questions in MyLabs Plus that say to simplify it, but write it in terms, if only I could spell simplified, in exponent form. But a lot of times we'll just say, like, for a simple number like this, where the exponent is sort of manageable, 2 to the 5th power, we could write it even more simply as what? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this should just be 32. Right? And you can explore that in your calculator just by going 2 to the 5th power is 32. And you could double check that, yeah, 2 to the 2nd power, whoop, and then make sure you come down if you have this kind of calculator, times 2 to the 3rd power also gives you 32. So these two expressions are equivalent to each other. They have the same value. One is just a simplified exponent expression, and one is completely simplified. It's just easier to say 32 instead of saying 2 to the 5th power. Now, for certain expressions, it'll be more simple to talk about it as 2 to the, or something to a power, right? So let me give you an example, like 10 raised to the 15 times 10 raised to the 25. Well, using this product rule, when we multiply numbers that have the same base, what do we do with their exponents?
Adding.
Add.
Yeah, so then we should have 10 raised to what power here?
40?
40. Yeah. And that would be good enough to simplify 10 to the 40th power, because if we tried to throw that in the calculator, 10 raised to the 40th power, you get this 1e to the 40. It's gone to scientific notation. Well, you can start to think about, okay, well, what if we took 10 times 10 times 10 times 10 and did this over and over 40 times. I'm not going to do it 40 times, but you can already see that I'm nowhere near, I've done nowhere near 40 tens, and I've multiplied them together and I've already gotten a really big number. Even if we did 10 raised to the 10th power, that's really big. 10 raised to the 9th power has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 place values, but 9 zeros. So this is going to be a number that has a 1 and then 40 zeros, but this is a lot simpler to write as opposed to writing such a large number. So we'll just leave this one because we can't manageably write it out as a long expression. We'll just leave it as an exponent expression. Does that make sense? Like the larger an exponent gets, the more compact we'll have to like write it. That's why scientific notation exists, right? To deal with numbers that are really large and really small. Okay, but I'm getting away from the point. The point is this product rule tells us in general that if I have some number raised to some power, so this is x to the nth power, and I'm multiplying it by the same base raised to a different power, so this is m, that what I do with those powers is I write the single base and then I add those powers. And we'll call this the product rule. But you have to make sure that these have the same base. Because, for example, can anybody tell me what 3 to the second power times, let's say 2 to the 5th power should be?
Three
Can
times
we-
3 times 2 times 2 times 2, 5 times.
Yeah. So if we were to do that and write it out, right? 3 times 3 times 2 times 2 times 2 times 2 times 2. I can't combine these into a single expression because we have different bases. So really, I have to leave them like so. What I can do is just go ahead and simplify them and say 3 times 3 is 9. 2 to the 5th power, as we found out, is 32. So I'm just going to have to multiply these together. I can't simplify it into a single exponent expression because I don't have the same base. And that'll be 288. All right. So let me give you some practice problems. Can somebody, well, I'll write them down, and then I'll ask you guys to simplify them. Okay. I should probably change this one to the 6th since we've already seen 2 to the 5th a couple of times. Okay. So what is 2 to the 6th power?
64.
64.
Yeah. 2 to the 5th is 32. So if we multiply that by another 2, we should get 64. And that's as easy as, throwing that into the calculator if we really, we're just not feeling it. What about this one? How can we simplify this into a single exponent expression?
3 to the 13th.
3 to the 13th power. Yeah. And then if we wanted to simplify that into just a single numerical expression without an exponent, well, here you probably wouldn't want to multiply 3 times 3 times 3 times 3 over and over until you got to 13. We would just throw that into the calculator, 3 raised to the 13th power, like so, and you would get this really ridiculously large number. Now, you could prove it to yourself, and I recommend that you do if this feels sort of unnatural, but it's just literally 3 times 3 times 3. How many of these do I need? Oh, God. I'm not going to do it. Oh, God, I'm doing it. Almost there. Yeah. Okay, so that's what I mean by like these numbers will blow up. We have a relatively small base, but you multiply it 13 times and you get this ridiculously large number, 1, 5, 9, 4, 3, 2, 3. And how would I read this? So I need a comma here, I need a comma there. 1,594,323 is equal to 3 raised to the 13th power. And that's just exponential growth. Like that's what scientists and people who study math and science mean when they say exponential growth. Think of this like you were doing a pyramid scheme. I'm not trying to pick on anybody who sells Herbalife, but I like to pick on Herbalife. Imagine that you had 3 friends and you got them in on your Herbalife scheme, and then they each went out and got 3 friends. And then they each went out and got 3 friends. If you did this process of getting people into the Herbalife, or it could be like a cult or something. Maybe we're all going to South America because we're going to Jonestown. I know that's a little bit dark, but that's where my head goes sometimes. If we get 3 friends and then they get 3 friends and they get 3 friends and they get 3 friends and we do that process 13 times, we've already got 1 million people that have joined our cult, right? Or you could think about it like maybe you have 2 rabbits that maybe that doesn't make as much sense, but they have a litter of 3, and then each of their litters, each of their offspring has a litter of 3, and then that continues so on and so forth all the way to 13th times. You would have 1,594,323 rabbits. That's pretty interesting. But mathematicians use exponents all the time to count really large numbers and to talk about these processes of exponential growth, and whether it could be rabbits in a natural population or bacterial load if you get some sort of bacterial infection. But anyway, that's my trying to make it real for you guys that exponents are not just like some magic that we do with numbers. It has some real world application. What should this be if we're combining this base of y? Again, it doesn't matter what number y is. We're going to use the same principle, this product rule. We can write this as an expression, y to what power?
24.
Yeah, if you added these up correctly, I have no idea. What is this? 8, and then that would be 8 minus 1, which would be 15. And then 15 plus 9 would be 24, yeah. And since we don't know what the value of y is, we'll just leave it alone as an algebraic expression that has an exponent. You guys have any questions about that? Does this seem pretty okay so far? Okay, I want to give you another example. I want you to think about it. What about 4a to the 8th power times 5a to the 7th power? What should this be?
Would it be 20a to the 15th power?
Yeah, that's exactly right. 20a to the 15th power. Is anybody confused on how we got this?
No.
Okay, good. But in any case, I'm still going to explain it. All right. So what's going on here is that, right, exponents are repeated multiplication. And in the past, we said that multiplication is commutative. That means that it doesn't matter what order you do the multiplication in. So if we're just strictly doing multiplication in this problem, and we have 4 times a to the 8th times 5 times a to the 7th, then I can just reorder this so that it has a more natural ordering. We could do 4 times 5 times a to the 8th times a to the 7th. And then we'll just simplify that, a little bit at a time. 4 times 5, we can just multiply those numbers and get 20. And then using our new product rule for these exponents when we have the same base, we just write the base and then add their exponents and get that 15. And then when we have a number or a coefficient times a variable term, we don't have to write the multiplication symbol. We can just write it as 20a to the 15th power. Does that make sense? Or is it still a little bit confusing? Or it didn't seem like it was confusing, but if anybody was confused, hopefully that's been cleared up. Okay. Well, sometimes we have to divide numbers that have the same base but different exponents. So we have this other rule called the quotient rule for exponents. And so let's think about this. Can anybody tell me what 2 to the 10th divided by 2 to the 5th is?
One power 5. I'm guessing. I really don't know.
That's a good guess. It's wrong, but it's really good that you're wrong. Does anybody else want to venture a guess at what this should be? Well, think about it like this.
1 to the 2nd power?
It should be what?
1 to the 2nd power?
Ooh, yeah, I see what's going on here. 1 to the 2nd power. That's another good guess. It's another wrong guess.
Okay.
But let's think about this, right? Let's think about the product rule, because like multiplying and dividing are sort of opposites, right? And with the product rule, we said that if we had, let's say if I had 2 to the 10th power times 2 to the 5th power, that we just wrote the base and then we added these two together, right? To get 15. Ooh, it's a little bit fuzzy. So if we're not multiplying, but we're dividing, what do you think we're going to do with the exponents? When we multiplied the exponents here, when we multiplied the bases here, we added their exponents. So if we're dividing the bases here, what should we do with the exponents? Subtract. 2 to the 10 minus 5 would be 2 to the 5th.
Oh, okay. It's because what I did is divide 2, divided by 2. And
You tried to divide it like it was a fraction, right? Cancel out the 2's, get a 1, and then divide the exponents.
No, I subtract.
You subtracted
But I
it.
say equals 1.
1/5. Yeah.
1 and the power is 5.
So we have to like make sure that our intuitions about fractions aren't getting mixed up with our intuitions about exponents, because remember, exponents are repeated multiplication. So if we wanted to expand the numerator and expand the denominator, we'll get a better look at what's going on here, right? What I could do with this 2 to the 10th power, I'm really wishing that I hadn't chosen the 10th power now. On the top is 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're multiplying all of those, right? Another reason why it's nice to have an exponent notation so that we don't have to write out the same number over and over again. And then on the bottom here, we should have 1, 2, 3, 4, 5 of these 2's. That's what we're really looking at when we write this expression with exponents. Well, now that we have it all written explicitly, this is just a normal fraction. And we have 10 factors of 2 on top and 5 factors of 2 on the bottom. And we can cancel common factors. So we can cancel this 2 with that one, this one 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 with that one. And then how many 2's do we have left over?
5.
5 2's. So when I said that they were good guesses, they were good guesses because you were trying to apply some rule about fractions and sort of making up a math. But here we really want to think about what is the definition for our exponents and then simplify from that. Okay.
So,
But
do you only subtract if the base is the same?
the base has to be the same because
Okay.
if we had, for example, let me choose a different number, 3 to the 7th power over, let's call this, what do I want to call this? 2 to the 4th power. And I were to rewrite this expression and expand it. So I'd have 3, that's 1, 2, 3, 4, 5, 6, 7. And those guys are being multiplied since that's the definition of exponents. At least the way we understand them now. 2, 2, 2, 2. Do any of these common factors cancel? Or do any of the factors cancel? Are there common factors? No common factors. So that's why the bases have to be the same for this quotient rule to apply. So in general, if we had x raised to some power n over the same base raised to a power m, then what we can do is write this as x raised to the power, and we subtract those powers. The top power minus the bottom power. All right. Do you guys want to practice the quotient rule a little bit?
Yeah, sure.
Yeah, let's go ahead and get some practice in. Let's do 4a to the 5th over 2a to the 3rd. And we'll do 2 will be 27 x to the 5th y to the 7th over 9 x y to the 6th. Yeah, I think that those will be 2 good examples. Does anybody want to venture a guess for this one?
2a to the second power.
Yeah. So I like to think about it this way in my head whenever I look at a problem like this. Go ahead and break it up into just thinking about the numbers and thinking about the variable expressions separately. 4 divided by 2 is just 2. And then if we use our quotient rule, we should have a, and then 5 minus 3 is 2. Is anybody confused on this one? I mean, another way you could work it out, right? If you wanted to know like the nuts and bolts of what's going on here, you could say that 4 is the same thing as 2 times 2. You could say that a to the 5th is the same thing as a, all over 2 times a, and then cancel common factors. So we have these 2's cancel, these a's cancel, and so you have 2 and then 2 a's left over. Right? So it makes sense if we just go back to the definition of exponents. But again, the quotient rule is really just a rule that's a shortcut so that we don't have to expand it out every time, because this is going to take up a lot of space and it's going to take you a lot of time on your homework and on the test. So we want to just get comfortable with the quotient rule. Was anybody able to solve this one or to simplify it?
I got 3x to the 4th and then y.
That's what I got too.
3x to the 4th y. Looks good to me. Again, another situation where I like to just say, let's look at the numbers. And then for each of the variables in the expression, right, we can just look at those separately. I don't have a third highlighter, so I'll just switch back to pink for the y's. And if you wanted to, you could call 27. Let's go the long way, right? Just so that it makes intuitive sense. 27 is 3 times 3 times 3. And then we have 5 x's. So 1, 2, 3, 4, 5. There's my 5 x's. And as the song states, they all live in Texas. Then we have 7 y's. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. See, again, this is why having exponent notation is useful, so that we don't have to repeatedly write these factors. 9 is 3 times 3. Then we have an x here, and we have 1, 2, 3, 4, 5, 6 y's. It's y, God. Okay. In any case, we'll cancel our common factors because that's how fractions work. Cancel these 3's. So we have 1 3 left over. Cancel our x's. So we have 4 x's left over. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we have this y left over. So 3x to the 4th power y. Make sense? Is that crazy? I mean, this is crazy. You don't want to do this, which is why we're giving you the rules, okay? All right. What about raising a power to a power? So for instance, what if I raised 2 to the 3rd power to the 2nd power? And this is a little weird. It's a little bit like Inception. Well, that would be written as 2 to the 3rd power in parentheses, and then we raise that expression to the 2nd power. What do you guys think that this should be if we wrote it as a single exponent?
Multiply the exponents.
Yeah, but why? So that's
Because
that's exactly right. 2 and then 3 times 2 is 6. But why should this raising a power to another power, why should it mean that we multiply the powers?
Because it's in parentheses.
Well, yeah, exactly right. So let's think about it that way. We can think about it like, oh, Kelly, you're saying that because it's in parentheses and parentheses imply multiplication.
Correct.
Okay, yeah, that's one way to thinking of it. But what the nuts and bolts of what's going on here is when we have something raised to a power, like 2, it says to take the base and write it 2 times and multiply it, right? It's just that in this case, the base is an expression that has an exponent, but we're still going to write 2 copies of it. So 2 to the 3rd power times 2 to the 3rd power. And then if we wanted to expand those, that would be 2 times 2 times 2 times 2 times 2 times 2. So how many 2's am I multiplying here? 6 of them. That's the real reason why the power to a power, you multiply the powers. Just going back to the basic definition of what it means to raise something to an exponent. Okay, so let me give you an example and see if you guys can figure this out. I'm sure you can. You guys seem to be a very smart, attractive, and quick-witted bunch. So what would x to the 3rd power raised to the 5th power be?
X to the 15th power.
Yeah. Again, these rules are just to cut down the time that it takes to process these expressions. We're going to multiply 3 times 5 and just call that x to the 15th power. Because we don't really have the time or the patience, right, typically to go ahead and write, and I'm going to do it just to show you how excruciating it is. We need 5 copies of this, so that's x to the 3rd times x to the 3rd times x to the 3rd. Good Lord, x to the 3rd times x to the 3rd, right? And then each of these can be broken down into x, 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 x. It's very adult content right here that we're dealing with. And then we count up how many x's we have here. 1, 2, 3, 4, 5. And there's 3 of them. So if we counted them, there would be 15, right? So why don't we just say that that is the rule in general? When we have something raised to a power raised to another power, multiply the powers. Okay, so now I'm going to try to break your brains a little bit with some more practice to try to challenge you guys. What do you think 3xy raised to the 4th power is?
Three x 4th power j. I mean, yeah, j 4 power.
Close.
Oh no, 3. Oh yeah, I had to multiply 3, 3, 3, 3.
Yeah, yeah,
Right?
exactly.
Yeah. Sorry.
Yeah, perfect. So whenever you have these terms or these factors inside the parentheses, technically they're being multiplied by each other, right? 3 times x times y to the 4th power. And so when you're multiplying inside this set of parentheses and you have an exponent that's being applied to each of them, then it's sort of like distributing, although mathematicians will get very irate with you if you call it distributing. But as long as you're multiplying in here, you can take this exponent and it belongs to every single term inside the parentheses. So we can write this as 3 to the 4th power times x to the 4th power times y to the 4th power. And since these are variable expressions, we can't really do anything with them. But we can simplify 3 to the 4th power using our handy dandy notebook or calculator. 3 raised to the 4th power is 81. And that should make sense because 3 times 3 is 9, and then 3 times 3 is 9, and 9 times 9 is 81. Okay, so we should get 81 x to the 4th, y to the 4th. Okay, what about negative 3 x to the 3rd? Can anybody tell me what that needs to be? Or what does it simplify to?
Is it negative 27x to the 3rd power?
Yeah, that's perfectly right. So again, we could say this exponent belongs to this term, the negative 3, and the x. Okay, so I'm going to apply that here and here and rewrite it. Now here you want to be careful with the negative sign. If you have negative 3 and you're raising it to a power, you want to enclose that in parentheses before you raise it to the power. Okay. Because if you do it without the parentheses in the calculator, you will get it wrong. Half of the time you will get it wrong. Okay, and then we'll have x to the 3rd power also. Well, negative 3 times negative 3 times negative 3, negative 3 times negative 3 times negative 3 is negative 27. So negative 3 raised to the 3rd power should also be negative 27. That's good. Negative 27. And since this is a variable expression and we don't know the value of x, I don't know what x is, x. We'll just leave it as x to the 3rd power. Okay. Okay, class, okay. What about negative 3x to the 4th power? What should that be?
Eighty-one x 4th power. Maybe.
81?
Yes,
Yeah.
positive.
Yeah, positive, right? Did anybody get something different? Did anybody get negative? Okay, so that's good. We could apply this and work it out the same way. Once you get fast enough, you'll just throw it in the calculator and say negative 3 times a raised to the 4th power is going to be positive 81. Negative 3 raised to the 4th power, and then x to the 4th power. And that's positive 81 x to the 4th power. Is anybody confused as to why this one's positive, while the last one was negative? Well, let's just make a note here. Because you'll want to keep in mind what signs we're going to have when we raise something to a power. So let's look at this example, or this set of examples. This is an A, even though it doesn't look like one. Negative 1 to the 3rd power. Well, what does that simplify to? What should we be able to simplify -1 to the third power to?
It's -1.
Yeah, that's just -1. And what about -1 to the fourth power?
It becomes +1.
Yeah, it's +1. What about -1 to the fifth power?
Negative.
-1.
-1.
And then what about the sixth power?
+1.
Okay. What about -1 to the 2057th power?
Is it a -1? Because it's an odd number?
Yeah, exactly. -1. Because the exponent is odd. Nobody has time to actually multiply -1 by itself 2057 times. But it should be noted that when you have a negative number raised to a power, that the negative number raised to even powers are positive, but a negative number raised to odd powers are negative. So that's the thing that you should note. And again, this note is just like a property that we discovered, we stumbled upon, that it tends to be really useful if you just remember it, as opposed to actually multiplying a number 2057 times and trying to figure out what the sign is supposed to be. Like if this was a -3 raised to this power, I wouldn't know what the value is, but I know that the sign of it would be negative. Okay, so let's do some more examples. Well, actually, before we do practice, let's look at some, we haven't seen fractions yet, right? So what about fractions? Well, if we had 1/2 to the fourth power, what do you think this will simplify to? Does anybody have a guess?
1/16, and 1 on the top and in the bottom 16.
Yeah, 1/16. That's perfectly fine, right? Because you could do this in a couple of ways. going back to just what the definition of an exponent is, it says write this base 4 times and multiply them. So 1/2 times 1/2 times 1/2 times 1/2. And then how do you multiply fractions? You multiply the top. 1 times 1 times 1 times 1 is just 1. And 2 times 2 times 2 times 2 is just 2 to the 4th power, which would be 2 times 2 times 2 times is 16. Alternatively, what you could do if you're dividing something in here is say that this 4 belongs to both the numbers or the bases on the top and on the bottom. So you would get 1 to the 4th over 2 to the 4th, and 1 times 1 times 1 times 1 is still 1, and 2 to the 4th power is 16. So either way you choose to interpret that, you'll get the same answer. I think that if this exponent gets larger, it becomes more time intensive to write out all the copies. So this is generally the way I think about applying that rule, that when we raise a fraction to a power. So we've sort of learned power rules now. The first power rule that we have is that if we have x raised to some power and we raise that to another power, we found out in general that we'll multiply those powers. And I call this one the power to a power rule. And even if we had more powers, you would just keep multiplying the exponents. Okay. We found that if we have, let's say, a times b, two different things, or two or more things inside the parentheses raised to a power, that we can write that as a to the nth power, b to the nth power, that they both get that power. And this is a power of a product because we're multiplying the stuff inside the parentheses. So each of them gets the power. And then we see with fractions, fractions are like division problems, that if we have a over b, and those are two different bases raised to a power, that we can rewrite that as a to the nth and b to the nth, that power belongs to both of the top and the bottom of the fraction. And we'll call that the power of a quotient. Okay, now let's practice some stuff. Let's go ahead and do x to the second, y to the ninth, raised to the third power. What should that simplify to? Similarly, 4x to the second, y to the third over 2, we'll call this x to the, we'll just leave it as x, and z to the fifth. And we'll raise that all to the 7th power for some reason. a to the third power over b to the fourth power and raise that to the fifth power. So let's see if we can simplify these. Nope, that doesn't work. Does anybody have an answer for number 1?
I put x to the 6th power and y to the 27th power.
You said y to the 27th power?
Yeah.
Yeah, that's right. Because all we're going to do is take this 3 and it gets applied to each of these two terms in here. But since we have a power raised to a power, we have to multiply those powers, right? So 2 times 3 is going to be your x to the 6, and then y to the 9th is going to be raised to the third power, which will be 27. So again, just be careful with that. This expression here and this expression here both get that power, but then we fall back on having a power raised to a power. Does anybody have questions about that one? What about number 2? Now, I will tell you that there's many ways to go about solving this, but some ways are a little bit more, have more steps. Let's put it that way. Was anybody able to work this one out?
I put 2x y to the 3rd power over z to the 5th power.
You said z to the what power?
5th? Is that a 5?
Yeah, that's a 5 down here. To the 5th power. Well, I can tell you already that this one's not right, but that's okay. Don't worry about it. This one takes a little bit of processing, and I unfortunately didn't give myself enough space to actually do that processing. So let's go ahead and take this to a different sheet of paper. We have 4x squared y to the 3rd over 2xz to the 5th power in parentheses, and then that's raised to the 7th power. Now, my approach to this is going to be bringing back order of operations a little bit. Okay, so if we sort of remember the good old days from the beginning of the semester when we were talking about GEMDAS, the order of operations, we said do the stuff inside the parentheses first. So what I mean by that is we can simplify. If we can simplify the stuff on the inside of the parentheses, then let's do that. And then we'll move to the exponents. So PEMDAS doesn't go away. In fact, it can help you simplify this expression. So let's look at the stuff in here, right? Can we cancel any common factors or use our quotient rule to reduce some powers? Well, 4 divided by 2 is just 2. If I have x and x here, and I know that x is the same thing as x to the 1 power, just by the power of 1 rule, then that means I can subtract these powers since I have x. So I have x, and then 2 minus 1 is 1. I still have a y to the 3rd power up there, and I still have a z to the 5th power there. So I've simplified the stuff on the inside of the parentheses, but I just still have this exponent that's lurking, right? And I need to go ahead and move on to the exponents next. So I can go ahead and apply and say that this exponent belongs to each of the terms inside of the parentheses. So I should have 2 to the 7th. If I have a power to a power, I multiply those powers. So I should have x to the 7th, y to the 21st, and then z to the 35th. Now, the variable expressions we have to leave alone because we don't know what the value of the variables are. But 2 to the 7th power, we might be able to reduce that just using the calculator or simplify it. So 2 to the 7th is 128. So we can just call this 128 x to the 7th, y to the 21 over z to the 35th. And then since there's nothing else we can do as far as simplifying goes, we're just going to have to leave it there. That make a little bit sense? Did it go a little bit fast?
Yes.
Are there any questions?
No, I pretty much just completely disregarded the 7 on the outside of parentheses.
Ah,
I didn't even write it down.
I see. Yeah, I always tell students that if you don't write down the problem correctly, you won't get to the answer. And that's always like super frustrating, especially if you work on a problem for like several minutes and then you realize, oh, I didn't write it down correctly. Okay. So let me go ahead and say that this one is supposed to be 128 x to the 7th, y to the 21st over z to the 35th. And so now you have a couple of, exponent rules that you can dazzle your friends with at your next party, at your next safely socially distanced party where everybody's wearing masks. Okay, did anybody get an answer for number 3? Did we simplify that one? That one was a little bit more straightforward.
15 over b 20 power.
Yeah, a to the 15th power over b to the 20th power. Boom. Okay, now I know that usually around this time we take a break, but we only have 2 more exponent rules to learn, and then I'm going to let you guys go. So I think that as far as exponents and powers are concerned, let us, wait for it, power through these next two rules, okay? Oh man, this was one of my favorite rules. This is actually the best part of the day. Power of 0. Can anybody tell me what 2 to the 0 power is?
It's either got to be 2 or 0.
Well, we hedged our bets. We gave 2 answers. And I will tell you that both of those answers are wrong. Does anybody have any other guesses for what this, if we simplified this, what should it be? 2 to the 0 power.
0.
Well, that's not right. It shouldn't be 0.
It's gonna be 1.
2.
It's not 2. It's not 1. No, it is 1. It is 1. I lied. It's 1. Does that seem strange?
Yes.
Yeah. Yes, it does. It seems strange to me too. Okay. Now I could just tell you, wave my hands and say, well, that's just the definition. We define anything raised to the power of 0 to be 1. But there's actually a more satisfying explanation as to why this exists. Now, I said that the definition we've been using for exponents is repeated multiplication, that the exponent of the power tells you how many times to write the base. But I haven't written anything here that resembles the base 2. So let's explore the exponents for a little bit and think about this pattern that we can get from the exponents. Well, for our positive exponents, or our integers, we said that if we had 2 to the 1 power, the exponent tells you how many copies of 2 to write. So we just write it once. And then 2 to the 2nd power, so I'm going up in exponent, says we need to write 2 times and multiply it. 2 to the 3rd power is 2 times 2 times 2. 2 to the 4th power is 2 times 2 times 2 times 2. And so you notice that every time we go up in power, we just put another copy of 2 onto the last row, right? Essentially, as we go up in this direction, we multiply by another factor of 2. Okay. And we multiply by another factor of 2 here, and we multiply by another factor of 2 here. So if we were going in the reverse direction, 2 to the 0 power, well, really this would be, maybe I've written this down a little bit weird. Let me go ahead and amend this a little bit. Started with 2 to the 1 power, and that's equal to 2. Don't mind the space. 2 to the 2nd power is 2 times 2, which is equal to 4. 2 to the 3rd power is 2 times 2 times 2, which is equal to 8. 2 to the 4th power is 2 times 2 times 2 times 2, which is equal to 16. And here it's going to be easier to establish this pattern that we have when we go in this direction. We're just multiplying by another factor of 2, or by whatever that base is. So naturally, what should 2 to the 5th power be? Yeah, it should just be 32, because we're just multiplying by a factor of 2. But if we walk in the opposite direction, because we're trying to figure out what 2 to the 0 power should naturally be. So we can start at 32, And if we walk down exponent, so from 5 to 4 to 3 to 2, right? What we're doing is really dividing by 2 by walking in the opposite direction in terms of our exponents. And 16 divided by 2 gets us back to 8. And 8 divided by 2 gets us back, oh, this is a 2. 8 divided by 2 gets us back to 4. 4 divided by 2 gets us back to 2. And so what should we naturally get here if we just divide by 2 and get to the exponent of 0? Well, what is 2 divided by 2?
1.
1. That's why it makes sense to call 2 to the 0 power 1. Another way of thinking about it is that if I had 2 to the 1 power divided by 2 to the 1 power, then by my quotient rule, I should get 2 to the 1 minus 1, which is 2 to the 0. But I already know that 2 divided by 2 should be 1. So that's another way of thinking about it. Our sort of natural extension of the exponents to the exponent of 0. Because when we have exponents that are integers or whole numbers and they're positive, it's easy to think of it as repeated multiplication. But that's not the whole story for exponents, because we see that repeated multiplication doesn't make any sense for the exponent of 0. So you could just remember this fact, or you could just come up with this pattern yourself. Okay, so then naturally, what should, let's assume that we had a negative exponent. What do you think 2 to the negative 1 should be? Now, again, we can't really think about repeated multiplication here, because how would I write the number 2 a negative number of times? It doesn't really make any sense. But what if I just continued this pattern, going in the opposite direction, walking towards the negative exponents? I could just take this answer and divide it by 2. And what is 1 divided by 2?
0.5.
0.5.
1/2. or
1/2. And
both
1/2 is just 1 over 2, right? Yeah. So if we wanted to represent it by a fraction, we could just call this 1/2. And that would be a natural extension of this pattern. Notice that this is not negative 1/2. That when we have a negative exponent, we still have a positive simplification. But what this negative exponent is actually doing, it looks like it's flipping our base to the reciprocal. So that's another note that we might need. Negative exponents flip the base to its reciprocal. So then if we continue this pattern, what should 2 to the negative 2 be? Well, we could take 1/2 and divide it by 2. And what should we get? It might be useful to think about it as a decimal for sure. If we had 50 cents, what is half of 50 cents?
25 cents.
25 cents. Something that we would call a quarter. Right? And you can sort of think about this as like the pizza analogy at this point. When we had 1, We had a whole pizza. This is my pizza. And then when I divided that by 2, I had half slices of pizza. And if I divided that by 2 again, quarters. So can anybody guess what 2 to the negative third power will be?
An eighth?
Yeah, 1/8. And 2 to the fourth power, a negative fourth power?
One 16th?
Yeah. But notice something about this little pattern that I've established, right? If we start at the middle, which is like 2 to the 0 power, we have 1. And if we go up, we get 2, 4, up in exponents, positive exponents. We get 2, 4, 8, 16, 32. But if we go in the opposite direction, we're really dividing. So we get half, 1/4, 1/8, 1/16. And what should 2 to the negative fifth be? Well, it's 1/32. So there's something interesting going on here. Because 2 to the fifth is 32, but 2 to the negative fifth is 1/32. And that's where this little note that the negative exponent flips the base to its reciprocal. Because I want you to think about the negative sign here for the exponent as performing the action. This negative performs the action of taking the base and flipping it.
I don't know if you can hear me, but you froze up.
Oh, how am I doing now?
I can hear you now, and I can see you moving.
Okay, so I want you to think about this negative exponent as flipping the base of 2. So we can take 2 and write it as 1/2. And then we can apply our exponent to that. So the negative exponent flips the base to the reciprocal, and then you still apply that positive exponent that's left over. And 1/2 times 1/2 is 1/4. The same thing here. We'll flip to 1/2. That takes care of the negative sign. And then we'll raise that to the third power. And sure enough, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. Flip the base with the negative exponent. Keep that positive exponent. 1 times 1 times 1 times 1 is 1. 2 to the fourth power is 16. So the negative exponent is performing the action of flipping the base. Okay. Don't make the mistake of thinking that because you have a negative exponent, you're going to have a negative answer. It does something different in the exponent. You still have positive answers or values because the base is positive. Okay, so those are the last 2 rules that I wanted to leave you with. The 0 power rule is that anything raised to the 0 power is 1. And the negative exponent rule is, you can think of it 2 ways. One is that if you just have a whole number raised to a negative exponent, that you should flip it to the reciprocal and then apply the exponent. So you'll have 1/x to the n. But this is easier to see if you just have a fraction. So if you had a over b raised to the negative nth power, then what you get is b over a raised to the nth power. And then you can apply the quotient rule to get b to the n over a to the n. Okay. Okay, so that basically covers this next section that we're going into. I believe that the homework is R.3 in MyLabs Plus. And it's all about applying these exponent rules. So I know that most of you guys, because you're still working on getting prepared for the test, you'll be focused on that. This homework won't be due until next Wednesday. So when the test is due. Maybe next Friday if you guys message me and say you need more time. That's fine too. But what I don't want us to do is get too far behind, right? So make sure that you're focusing on getting prepared for the test, getting that out of the way. You'll be in good shape if you can complete test 1 by the weekend, but it will remain open through Wednesday, okay? Through next Wednesday. Just make sure you pace yourself, that you're getting in there and applying yourself so you don't fall behind. So as always, I'm going to let you go now, but if you do have questions and want those answers right now, you're more than welcome to hang out. Otherwise, go forth and good luck on your test. I'll see you guys in Math World, hopefully.
Sir, I have a question.
Yeah, a question?
Do we need to have all the notes, or can we have like some of the notes? Some of the notes I didn't get to get.
The ones from today?
Yes.
I'm going to be posting these. I don't know if you guys have been checking the lecture videos when I upload them, but I also post the notes that I write down here. So if you ever miss something, or if we went too fast, you can review not only the video, but these lecture notes that I've written down.
And we need to write them down, you said, right? And then submit them to you?
Your notes, like for that you're taking in class?
Yeah, I saw a post that he had said something.
No, so I'm not picking up your notes. Those are for you to study, right? I assume that you guys are listening and taking notes while we go through the lecture. But what I need from you guys when you take the test is to work out each problem to the best of your ability on your own sheet of paper. And then you're going to need to upload that document.
Oh, okay.
And whatever note sheet that you make, like your study guide, that needs to be uploaded as well for the test.
Oh, okay.
Right, not your general notes that you take for the lectures.
Oh, okay. And then you said it needs to be scanned?
Yes. So that's why at the beginning of the semester, right, first week, we had that cam scanner assignment to see if you guys had the scanning ability, either through cam scanner or some other, if you could have a computer scanner that works. Some way to scan and upload your documents to Canvas.
Well, I still don't have a computer, but I'm gonna borrow someone's.
Okay.
I'm not sure if they have cam scan. I mean, I can always download it, right? And then
Right, Cam Scanner is just a phone application. There's a free version, so if you get hit with ads that say, upgrade to the premium for blah 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 money, you can just X that out because the free version works just fine. But
okay, so you would scan it and then have it sent to you.
Upload it to Canvas. There's a form.
Okay.
Yeah.
Oh, okay.
So you'll want to look at the instructions there in the module that I called Test 1 in Canvas, because all the instructions for this are there. But if you do have any trouble, you can message me at any time.
Okay, sir. Thank you. Sounds good.
Any other questions?
Well, yes, I have one question.
Sure.
Always, sorry.
No, you're fine. This is what I'm here for.
No, I'm just like, I don't have a calculator. I use calculator. I use my phone. But in this case, to do the test, we need a calculator, right? Not the phone calculator.
I'm going to be 100% real with you. it would be ideal if you weren't using your phone because of the possibility of using your phone to cheat. But I can't control what you guys do or what calculators you're using at home realistically. I'm not a fool that thinks that, oh, I can force you guys to not use your phones.
No, I can go buy one.
No,
but
no, I don't want you to spend your money.
No.
So just honor code, just don't cheat, and then we'll be fine.
No, it's okay. I can buy just one simple calculator. The reason that I don't want buy the other calculator is
Yeah.
because I really don't know how to use it.
This is really powerful and way too expensive. So I wouldn't recommend getting anything like this if you're going to pick up a calculator. But it's useful to have one that has the exponent button.
Mm-hmm.
This one has fraction utilities too. If there's a cheaper one that you want to go out and get, that's fine. But again, I basically, maybe I trust my students too much. I think that we're all adults here, and I don't want you to spend your money needlessly on a calculator if you're doing fine with your phone. Okay.
Yeah, I can, like I say, I can buy something that is not that complicated for me.
Yeah, that's fine. However you want to do it. I'm not trying to get you to spend your money, but if you want to, then do it.
Okay, thank you.
Yeah.
Can you tell me what that exponent button looks like?
It's this like, it's called a caret, but it looks like a house, like an arrow pointing up.
Okay.
In fact, I don't know if you guys have Androids or what are these, iPhones, but if you're using your phone, let me demonstrate here, and you're using the calculator app. Right, this is what a lot of people's calculators look like. When your phone's unlocked and you rotate it, it turns into scientific mode, and nobody can really see that because of the glare. That's a little bit better. But there is a button here for exponents, but it looks weird. It's x to the y on your phone. So you could do, for instance, 5. Nobody can see that. 5. And then the x to the y button to the second power. Nobody can see this. And then equal is 25.
Okay.
That makes sense because 5 times 5 is 25.
I think I found, I don't have your calculator, but I think I found it on mine.
Yeah, and usually if you rotate your phone, you can get the scientific buttons, so that if that exponent button is not showing up, then try rotating it. But even with those basic phone calculators, like sometimes students have trouble with them. So if you need to see me in office hours or Math World, then we can like figure out how that works together. Because I'd rather you be equipped with some way to use a calculator to get the arithmetic done rather quickly, since you have only 2.5 hours to do the test. I think it's enough time. I think it's more than enough time. Yeah. Any other questions?
No, thank you. I'll see you tomorrow.
Yeah.
You said the test is 20 questions?
20 questions.
Okay.
Yeah. All right. If there's no more questions, you guys are free to go.
Thank
Thank
you.
you.
Thank
Have
you.
a good one.